Today I am going to teach you how to find out the value of minimum reflux ratio R minimum for a special case when the equilibrium line curvature is a little different. Okay, now to you know that calculation of R minimum is important in distillation column designing, and the standard method that we follow is the McCabe-Thiele graphical method. Okay, now let us assume that we have an ideal binary system of A and B. Okay, A and B forms an basically binary system, and the solution suppose is ideal. Okay, where A is the more volatile component and B is the less volatile component. Okay, now we'll see exactly how to plot various lines within the mole fraction diagram following the standard McCabe-Thiele graphical method. Now, in a standard mole fraction diagram, as the name suggests, we have the y-axis and we have the x-axis. You may show the subscript here, since A is the more volatile component, so obviously the data has to be represented with respect to the more volatile component, which is A. So basically you have y and x, then after that you join the two opposite points and make a diagonal. So this is nothing but y equal to x line, also it is known as 45-degree line. Okay, now after that one is supposed to draw the equilibrium line. Okay, just a minute. Now we have to draw the equilibrium line. Okay, now to draw the equilibrium line, either the experimental data will be provided, or if the data is not given, since it forms an ideal binary solution, one may use the standard Raoult's law, and where we come across an equation like y is equal to alpha x divided by 1 plus alpha minus 1x, this sort of a relationship where alpha stands for relative volatility okay of A with respect to B. Okay, so if the value of relative volatility is provided, one may put the number and can get a y equal to fx type relationship, and you can draw the equilibrium line. Okay, now suppose in this case the equilibrium data is given, the vapor liquid equilibrium data is given. Under standard situation, the nature of the vapor liquid equilibrium line is always concave downward type. Okay, now once you have the equilibrium line drawn, the next step is to draw various operating lines. Now in distillation column, we have two specific operating line. One is basically known as the enriching section operating line, the other one is the stripping section operating line. So to draw the enriching section operating line, we have to locate XD point, which corresponds to the percentage purity of component A in the distillate, and then you have to locate the bottom product composition of A and the feed composition XF. Okay, now from y equal to x line, the standard equation of enriching section operating line is just a minute, y is equal to r over r plus 1 x plus xd over r plus 1. So this is basically the equation of enriching section operating line, or EOL. Okay, so once we locate y1 equal to xd point on y equal to x line, by taking the slope r over r plus 1, if the value of reflux ratio is given, so one can easily calculate the value of the slope of the enriching section operating line. Or if the value of the reflux ratio is given, you know the value of xd, so you can find out the value of intercept and you can locate the value of intercept in the y-axis, and you may join these 2 points and you can get the end-reaching section operating line, okay, which can be abbreviated as EOL. Okay. Now suppose the feed which enters into the distillation column is at its boiling point. Okay, at its boiling point. Actually, we may have several feed condition, but the simplest to understand in graphical method is when the feed is at its boiling point. So what happens in that case? You all know the feed line will be a line of infinite slope. Okay, so it will be basically a straight vertical line emanating from XF point. So you can just draw a straight vertical line. So you can find out the point of intersection of end-reaching section operating line with the feed line. And obviously you know that the stripping section operating line must pass through the point of intersection between end-reaching section operating line and the feed line. So you can just simply join these 2 points and you can get the stripping section operating line, SOL, and this is basically the feed line. So this is how actually we normally draw various operating lines within the mole fraction diagram following the Machiavellian graphical method. Okay. Now suppose the value of reflux ratio is not provided. Now if the value of reflux ratio is not provided, the R value is not provided, so you simply cannot draw the end-reaching section operating line, and since you cannot draw the end-reaching section operating line, the point of intersection cannot be located, and hence the other operating lines, which is stripping section operating line, can't also be drawn. So in that case we need to resort to the concept of minimum reflux ratio. Okay, now in case of minimum reflux ratio, what happens? The same method. First thing, just a minute, let me just draw it in a better way. So yeah, so you have y-axis, x-axis. A stands for the lighter component or more volatile component, and then you have y equal to x line, and then you draw the equilibrium line, standard equilibrium line, which is concave downward. Fine. And then now you don't know the value of reflux ratio, so you cannot draw the end-reaching section operating line straight away. Okay, so what you need to do is that first you draw the feed line. First you draw the feed line from the XF point. The feed is at its boiling point. We have assumed that. Okay, so it will be a straight vertical line, and this feed line basically intersects this equilibrium line at this point. Okay, and then you draw the end-reaching section operating line in such a way so that it meets the point of intersection of the feed line with an equilibrium line, and then you find out the corresponding y-axis intercept. Okay, now exactly what is happening. So if you know that the value of the expression for end-reaching section operating line was y is equal to r over r plus 1 x plus xd over r plus 1. This was the standard equation. Now what happens, physically speaking, as the reflux ratio, we're supposed to find out R minimum, so basically reflux ratio is decreasing. Okay, so as the reflux ratio is decreasing, the slope of the end-reaching section operating line will also decrease. So basically this end-reaching section operating line actually move away from the y equal to x line and go towards the equilibrium line. This is what is happening in reality, practically speaking. Okay, so what exactly is happening? So once it just moves away towards the equilibrium line, so there comes a situation when this operating line, which is end-reaching section operating line, coincides with the feed line exactly onto an equilibrium line. Okay, and this point where this operating line and feed line coincides with the equilibrium line is known as pinch point. Okay, is known as pinch point. So first you find out the pinch point, and then since you know the stripping section operating line has to pass through the point of intersection between feed line and enriching section operating line, so you may just join these 2 points and get the stripping section operating line. So basically pinch point corresponds to a situation where both the operating lines as well as the feed line coincide with the equilibrium line, and we all know equilibrium corresponds to a condition where all the driving forces basically ceases to exist. Okay, so there is no delta y. Okay, delta y is 0, delta x is 0, so all the driving forces ceases to exist at the equilibrium point. Okay, now once you have this y-axis intercept, so you know that phi, the value of phi is nothing but xd over r plus 1, but since it passes through the pinch point, so r is nothing but r minimum. So if you can find out the value of phi from the y-axis, you know the value of xd, you can easily find out the value of r minimum. So once you can find out the r minimum, r optimum can easily be figured out. Okay, as per the thumb rule, it is 1.1 to 1.5 times, okay, r minimum. So you can find out the original reflux ratio and then can move on to find out exactly the number of stages for a given separation using the McCabe-Thiele method. Okay. Now, as I mentioned in the very beginning of this simple discussion, is that you were supposed to find out the value of minimum reflux ratio when the curvature of the equilibrium line is slightly different, not conventional. Okay. For example, suppose we have a case like this. Okay, so you have y equal to x line. Now instead of the regular concave downward, suppose our equilibrium line is something like this. Something like this. Okay, and we are supposed to find out the value of r minimum. So how to go about solving it? Okay, it's relatively tricky. So first thing first, so the feed condition was given, which is basically at its boiling point. Feed is at its boiling point. You have xd, you have xw. Now just let me just expand it a little bit. Just this is the feed point, suppose this is xw and this is xa. Now if the feed is at its boiling point, so what happens from the feed point, you draw a straight vertical line, and this is the point of intersection. Fine. And then as per the earlier practice, if you just join y1 equal to xd point from y1 equal to xd point, if you allow enriching section to emanate out of it, intersect the point of intersection between feed line with the equilibrium line, and you extend it. Okay, this was the earlier practice standard, and then you join the stripping section operating line. Okay, but if suppose the curvature is slightly different, okay, suppose it is something like this, and you extend the stripping section operating line in this way and then join. Okay, so the question is whether this value of phi is going to give you the value of r minimum. This is the question, and the answer is no, it is not, because this is a wholesome mistake if someone does follow the original practice. Okay, so in that case, what exactly is happening? Let me just show you in a proper way. A minute. So we have x, y equal to x line. Suppose this was the nature of the equilibrium line. Okay, concave upward initial phase and then concave downward. Okay, slightly the curvature is different from the convention. Okay, so in that case, if that is the scenario, if you just follow the standard method, okay, what was happening, suppose this is the feed line from the feed point xd. Suppose you join, and then suppose you have the xw point, and you draw the stripping section operating line. So one, if you follow the standard method, what exactly is happening, the stripping section operating line is basically crossing over the equilibrium line. Okay, and we know that under no circumstances an operating line can exceed and go beyond the equilibrium line. Okay, because equilibrium in a way means that maximum achievable under a given circumstances. Okay, so maximum mass transfer, maximum separation is equilibrium unless you shift the equilibrium. So at a given equilibrium point, whatever maximum mass transfer has to happen has happened, and unless you shift the equilibrium, no further changes are going to happen, and all the driving forces ceases to exist. Now if you follow the standard method, exactly what is happening, you have drawn the feed line, there is enriching section operating line, there is point of intersection which is supposed to be the pinch point, but the moment you draw the stripping section operating line, it is exceeding or going above the equilibrium line, and which is not possible thermodynamically. It is not possible. Okay, so there cannot be a crossover of operating line and the equilibrium line. So that is why the standard practice of finding out R minimum for a case where the vapor liquid equilibrium curve is having a different curvature. Okay, in that case you simply cannot follow it. So what one has to do, the method is simple. You have a mole fraction diagram, yx, yaxa, then you have y equal to x line. Suppose this is the equilibrium line. Okay, you have xf point, you have xd point. So what you have to do, first and then suppose you have xw point. Okay, now what happens, you first draw the feed line which is at its boiling point. Okay, it intersects. Okay, then after that you don't draw the enriching section operating line, rather you draw the stripping section operating line. So what happens, from y equal to x line, okay, you draw the stripping line which will be a tangent to the equilibrium line, and then you find out the point of intersection of the stripping section operating line with the feed line. Okay, and see, right now there is no crossover of stripping section operating line with the equilibrium line or with respect to the equilibrium line. So once you find out this point of intersection, then you can easily join 2 points to find out the enriching section operating line. So this becomes the enriching section operating line, this is the feed line, and this is basically a line which is tangent to the equilibrium line, is basically the stripping section operating line. Okay, and now you extend the enriching section operating line to find out the y-axis intercept, which is phi. So phi stands for xd over R minimum plus 1, and this will give you the right value of R minimum. So the summary of the whole discussion is that once you have a vapor liquid equilibrium data which forms a curvature which is slightly different from the conventional one, which happens to be concave downward, and if you follow the standard method, it's fine. But if the curvature is quite different, as I have just shown you for case 2, and if you follow the standard method, there may be a possibility where the operating line might be crossing over the equilibrium line, and which is practically not possible, not feasible. Okay, so in that case what you have to do, you first draw the feed line, then you draw the stripping section operating line which will be just tangent onto the equilibrium line, find out the point of intersection, and then you draw the enriching section operating line, extend it, find out the y-axis intercept, and correspondingly you can easily find out the value of R minimum. Now the question comes in case 2, which is going to be your pinch point. So this is going to be your pinch point, okay? So pinch point basically here is the point where the stripping section operating line is just touching the equilibrium line, okay, when you draw the tangent, okay? Not the earlier pinch line where I have shown that both the operating lines as well as the feed line is basically touching the equilibrium line. That's the standard conventional way of finding out the pinch point. But in a special case like this, your pinch point will be this one, okay? So yes, in a distillation column designing, the pinch point normally locates somewhere close to the feed point, because all the time these operating lines and feed line, merges with the equilibrium line in and around the vicinity of the feed plate, okay, in normal practice. But there can be cases where the pinch point location can be in the enriching section or maybe in the stripping section like this, okay? So thank you very much for listening to the whole lecture, okay.